Okay, so this is a differential equation that shows up when you're solving a simple harmonic oscillator for quantum mechanics. So you're trying to find the solution of the time-independent Schrödinger equation. And the potential is essentially a parabola. So you have V of X, we'll just keep it to X, 1D, this is what you're kind of used to seeing, the potential energy in classical mechanics, 1/2 kx squared. In quantum, you usually talk about this as 1/2 m omega naught natural frequency squared x squared. But it's the same thing because omega naught is root k over m. Okay, what's the difference in between the classical and the quantum behavior of this? So all philosophical, like all conceptual. What does a classical particle with some energy E do when I put it into this quadratic potential well?
It'll kind of bounce back and forth in one dimension.
Yeah, so it gets fast in the center, it gets slow at the edge, and it has what are so-called classical turning points that we can find by equating solving where I'll say xt for turning point, where the total energy is equal to all potential, which is to say no kinetic. And it just bounces back and forth forever and ever and ever. Okay, that's not what we're solving at all. So what does a quantum mechanical particle do when I put it in a quadratic potential?
It'll have like a wave function, which is probably going to have like a higher amplitude inside the well, but like we'll have like tails going out into the, if it's an infinitely high potential well, then it'll kind of like drop off pretty fast at the edges. But if there's something on the other side, it might kind of come back.
Exactly. So you get to go into what's called the classically forbidden region. And the ground state is actually I'm gonna ruin the suspense. It's just a Gaussian. But you have a probability distribution given by the norm of the wave function squared. But basically the point is, instead of solving for a classical trajectory, we want to solve for a wave function. And because we're in 1D, we have a wave function of just x. So this is the ground state. So there could be a first excited state, which actually would look like this. And then, except I can't draw it, and a second excited state and a third excited state. So ultimately what you're doing is you're solving eigenvalue problems, right, that are separated by finite values of energy. So this is what we're going to do. Ultimately, what turns out to be true is we end up with solutions or wave functions. And we're going to label them with a subscript n, where n is the nth energy state. And these things are crazy. They can go into the classically forbidden region. And what's also true is we have a discrete infinite spectrum. So in the classical problem, you can put in any energy you want. Like I can give the ball bouncing back and forth any amount of energy whatsoever. In the quantum problem, you're going to end up with a discrete spectrum. There are only certain quanta, one might say, of energy that you can put in. So these are the things that are going to come out naturally. You know, it seems really weird because that all sounds like physics and it's like kind of woo-woo physics. This will all come naturally out of solving the differential equation with the appropriate boundary conditions, which is kind of neat. So ultimately, you'll see all of that coming out of what's called the method of Forbinius. One last note, why is classical or quantum, why is this the most important problem in all of physics? And maybe I'll try to kind of troll you guys a little bit by saying like, well, you know, I think this is silly because if I were to look at a real potential landscape, like in real life, it might look really complicated like this. What do you guys see when you look at that?
You can separate that into a bunch of different like quadratic wells.
Exactly, right? So it's, and you know, part of that, you're not wrong if you criticize this as like physicists are just trying to solve the only problem they know how to solve. It's like, yeah, there's something about that. But the other thing is that you have two possibilities. Either the particle goes off forever and it's free, or the particle is bound and has some stationary state. You know, like if a planet is orbiting around a star and has done so for 1 billion years, it's stable, right? So anything that's stable can kind of be described locally by something that to first approximation looks like this. This is really like the most important problem in physics. Anything that's stable, the first pass you can make it describing its motion is through a quadratic. The other way of thinking about it is like if you really like Taylor's theorem, I have some equilibrium position, right? And my potential I can describe if I just take a Taylor series like this. Where this is evaluated at equilibrium, well, that's 0. So I get a constant term, which I don't care about, and then the first contributing term is a quadratic. So again, super important. Okay, and turns out you can identify the second derivative of the potential with the strength of this. You can either identify it with K or omega naught, however you feel like doing that. Okay, so really important. We're going to set this problem up for the time-independent Schrodinger equation. And there's going to be a lot of stuff in there. So we'll kind of split this up into 2 parts. So the time-independent Schrodinger equation, again, should really remind you of an eigenvalue equation, except phi is a function, so we call it an eigenfunction. So we have a differential operator h, and it acts on the wave function, which is a solution, and then I get the wave function back, and it spits out its energy. So really cool. And in this case, h, this differential operator is minus h squared over 2m. Unlike when we talked about this just a couple of minutes ago, we're in 1D. So the Laplacian in 1D is just 2 x derivatives. So really nice, comparing that to the full spherical polar Laplacian. So this is our differential operator. And I could write down the whole thing like this. And what you would realize is just up to some kind of fugly constants. So the primes, we only have one variable, so the primes need to indicate derivative with respect to x. We're solving this differential equation. So call this star. Okay, so what I'm going to do before we launch into this is, in general, if you're confronted with a completely new differential equation, and imagine that you're on a desert island, right? So no no connectivity, no books. And you don't recognize its form immediately. And that's kind of the game we're pretending to play right now, is there are two things that you should always do. So this is a physics differential equation, which means it's got a whole bunch of junk in it. So our two kind of evergreen steps is that one, we will like clean up all the constant mess. So all the physical constants. And you know that you've done this right if instead of x, you can figure out, and I don't know if I can even draw a psi in this. Yeah, there's a good looking psi. You know you've done this right if you can get things to be unitless. So cleaning up the constants, turning this into something that you might see in a DiffEq textbook is a good idea. And then two is you have no other techniques available, right? All you know is that I'm pretty sure that psi should be like well-behaved. My wave function should be well-behaved. How about try a power series, right? So Taylor's theorem works both ways. If you have a function and you just care about part of it that's well-behaved, you can just look at its local power series expansion. If you don't know the function itself, but you know it's well-behaved, you can also say like, well, why don't I try to find out what it is through its Taylor series, right? So this is what we're going to do with the last set of differential equations we talk about in this class. So Bessel's function, modified Bessel functions, and then here to get the Hermite polynomials. So let's just try to solve this by cleaning it up and then saying, well, maybe I don't care about this function. I just want to like find its power series. So we'll do those two things. This is what's kind of grandiosely called, I think mostly it's called method of Forbinius, because Frobenius's method is just really awkward to say. Frobenius. And that's worth a slight aside as to how that works. So let's say that I have some differential operator acting on some function, and we can clean up star so that it looks like this. So, and we want y of x, right? So y is our unknown function of x, and d is some differential operator. And we know that y of x is so-called regular, which means the differential operator, it might have some function of x in it, that doesn't blow up, and we know that our function doesn't blow up either. And if it, you know, the point you care about, some regular point isn't zero, you should shift your accounting so that it is at zero. That means we can expand around zero. So essentially just say, all this is just a complicated way of saying is, let's just kind of solve this, not function first, then power series first, and then maybe we can even back out the function itself from this. So assuming a power series form, and if, you know, you have to, and you can't, you know, there's something really, whoops, there's something really naughty about x equals 0 and you can't shift. No, that was okay. Shift away from it, then you would say x minus some regular point to the kth power. but that won't be us. And what's going to end up happening is you just plug this thing in and you will end up with algebraic coefficients or algebraic equations on the A of k. So each A of k sorry, there's a little like bar at the bottom of my screen, so it's going to look really gross. So the A of k satisfy algebraic conditions. And in the case of the simple harmonic oscillator and Hermite polynomials, they're really nice ones. So that's going to be our program for this. So first we're going to clean it up, and then we're going to say like, look, I know I have a well-behaved solution, so let me just start with the power series of it, plug it in, and you'll see some magic start to happen. Okay, so any questions about our program? Okay, here we go. Toss all of this. And step one is clean it up. And ultimately what we want to do is have everything be unitless. So this is more of like a physics consideration than anything. So we're going to take our simple harmonic oscillator equation of motion and just, think really hard, do some scratching, and it turns out that this, so kappa defined as 2e over h bar omega naught, you're like, well, 2 is unitless, why'd you put that in there? And my answer is like, trust me. And then that's just a constant. And then our x variable will choose to be m omega naught over h bar x. Okay, and so this is something that's kind of done with like the malice of people doing this for years and years. To write it out explicitly, what this does is this turns star into this, much better behaved. Might regret choosing psi. So kappa is just a constant. And then I'm going to write this once and only once. From here on out, derivatives are derivatives with respect to psi, because that's our variable. And phi is now written in terms of psi. So this really is the time-independent Schrodinger equation for the for a quadratic potential for the simple harmonic oscillator. It's just we cleaned up all of this. And so this is nice. This looks like something we might find in a differential equations textbook. And from here on out, this is now phi double prime psi minus kappa phi. So this is really, really nice looking compared to what we started with, right? Okay, so that was step one. Step two is assume that we can represent phi of psi as, again, think about Taylor series. And this is the point about being quote unquote regular. So we're gonna have one example of something that isn't, is that if there is a blow up somewhere, we wanna give ourselves the possibility of allowing our function itself to blow up. So the most generic way you can implement the method of Forbinius, the power series method, is like, okay, but there's some constant where I can have like 1 over psi terms or 1 over x terms or whatever you want to call it. So this is the general solution for us. Our phi does not blow up, so r equals 0. You could have a case where something does go to a singularity, in which case r might be equal to 1 or 2 or something like that. But this is the most general way of writing stuff, okay? So we could just plug stuff in right now and we would get some algebraic conditions. What you can see by kind of looking at this is that each one is going to relate a term. So I have times psi, and then I have two derivatives. I'm going to have a term that relates something to a term that's two xi's below it. But then I also have this weird kind of relating psi to itself through the multiplication of psi squared. So this is going to be possible. It's going to be like kind of hard to deal with. To make our lives easier a second time, we can look at asymptotic behavior. Because we know what this is going to look like as psi goes towards plus and minus infinity. So what should I get at plus and minus infinity?
Should tend towards 0.
Yes. Yeah, and you can see that directly here because if psi is equal to infinity, phi needs to be 0. The other way of thinking about it is just like, you know what the physics is. So you know that this thing should, you know, even though it manages to kind of like sneak into the classically forbidden zone, we should definitely have this thing vanish at plus and minus infinity. Okay. So in that case, in the asymptotic limit, this psi squared term is going to be much, 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 much bigger than the kappa term. So the asymptotic behavior is going to be this differential equation. And this thing has solution a e to the minus psi squared over 2. Right, so one derivative will pull down a psi, the other derivative will pull down another psi, and then we're left with the thing itself. Okay, so it turns out that this, you don't need to do this, pull out the asymptotic behavior. But in this case, because the asymptotic solution is an exponential, which has an infinite number of terms, it's going to save us a lot of work and fussing through infinite number of terms and recognizing this exponential inside of the polynomial. So essentially, this is going to make things much, 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 much easier, but it doesn't, you know, turn impossible into possible. Okay, everybody with that so far? Okay. So now what we're going to do is we still have our nice clean version of the time-independent Schrodinger equation, and we know that our asymptotic behavior is dictated for us because this thing has to go to 0, but it still has to, even as it's going to 0, it's got to obey this equation. So we have our final trial form. And now we're going to Forbinius this. So the final nice form is cleaned up and unitless, and asymptotic behavior is picked off. It's going to be phi of psi equals the part that we don't know and is going to be really important in the center. And then the part that we already know is going to be relevant. It's going to die this fast at the edges. And that last unknown bit is the part that we're going to power series. Oops. Okay, Okay, so this is in some sense our trial function. Yeah, you can also think about the method of Forbinius as not anything fundamentally new or distinct. Is that honestly, how did you solve most differential equations? It's just like you stared at the thing for a while and then you said like, this is my trial function. Like if you knew your answer should wiggle, you should use trial functions as sines and cosines. You know, if you know your trial function should die at infinity, you should use an exponential. This is no different. This is just kind of a systematized way of doing that, where, you know, the less you know about the trial function, the more likely it is that a power series expansion is, you know, it'll get you where you need to go. Okay, so this is where we're at. Any questions about that before I clean this up and then we just go for it? Okay. So we have trial function. And differential equation. And we take one derivative. So I take one derivative of this. And remembering that we just called this whole thing. Just for shorthand, we can call this whole thing h of psi. So product rule says I get an h prime, and then I get the stuff that comes out of the exponential. And each one will end up with the exact same exponential. So that's one derivative. And then two derivatives. I swear this is the easiest way of solving this. We have h double prime, and then we have two of these terms. Then we have, I think, plus psi squared minus 1. This is just doing the calculus and remembering that h depends on psi. So you have h term and an h prime term. So now I have everything to plug into the differential equation. I have h double prime minus 2 psi h prime plus psi squared minus 1 minus psi squared over 2 equals psi squared minus kappa h e minus psi squared over 2. Oops. That is not perfectly legible. There. Okay, so that's just taking the derivatives and setting things equal. And you can see the first kind of miraculous payoff from expressing this in terms of its asymptotic behavior. Things got a little bit gross in the middle, but we can just do this. Right, so the exponential part goes away. And then we can pack everything on one side. And what we get, ordering terms in terms of the h's, because we're going to expand that next, h double prime minus 2 psi h prime plus kappa minus 1 h. So when we were doing that, another nice thing canceled out. We had xi squared here and xi squared there times h. So honestly, like this is the time-independent Schrodinger equation for the simple harmonic oscillator. And at some point somewhere in some Diffie-Q book, somebody might say like, yeah, the time-independent Schrodinger equation for the simple harmonic oscillator. And you're like, I don't see that there. Okay. So now we need to figure out what h and h prime are. So h of xi, this is the part where the algebraic equation comes in, is that this is going to have terms, this is going to have terms, and this is going to have terms. And this will have an ak, an ak minus 1, and an ak minus 2 that we get to relate. Okay, so that's true, which means that h prime of xi is equal to just the derivative of a polynomial. So k, a, k, xi, k minus 1. And then likewise, h double prime is equal to some k from 0 to infinity, k times k minus 1, ak, ek, xi, k minus 2. Right? So just taking derivative. What I can note though is because when k equals 0, this term doesn't do anything, right? Because when k equals 0, this vanishes. And likewise, when the bottom term, the h double prime term, k equals 0 or k equals 1, this vanishes. I can just re-index things in a way that makes things a little bit nicer. Is I can just throw away the 0 term and then reorder it starting at a new 0. So basically shift 1 up because the first term listed in this way is 0. So k plus 1, ak plus 1, xi k. And the reason to do this is that it lets me make an easier apples to apples comparison in between the xi of k terms. So likewise, this thing can get shifted up by 2. And now I have everything written in terms of xi of k's. Okay, so we don't need our trial function anymore. We don't need our differential equation anymore. It's already been, we've dumped everything in. The only thing we have to do is take this is the differential equation written in terms of our trial function, and then put in these values and do some algebra. And the fundamental insight that you need to make to figure out where this thing comes from is that if I give you an algebraic equation that looks like this, something that people kind of glibly talk about in terms of, like, well, if I have one equation, I only have, I have one equation with 2 unknowns, I can't solve it. Or I have 4 equations with 5 unknowns, I can't solve it. Is that really true? I have this and it's true for all x. So every single real number that you can think of. X is 4, x is minus 17, pi squared over e or whatever. So this kind of bumper sticker slogan about 4 equations, 5 unknowns or whatever, be very careful here. Can you tell me what A and C are from this one single equation? What's A?
It's 2.
And what's C?
It's 1.
Yep.
So
negative 1. Yeah, and this is true because this is really an infinite number of equations, right? This is true for x equals 1, x equals 2, x equals, pi over 70, whatever. So what we're going to do is we're going to compare term by term, right? So what you did is you compared the unknown coefficient on the x squared term with the known value on the x squared term. And what you did was you compared the unknown coefficient on the constant term with the known coefficient on the constant term. So if this is true, this thing in the pink box is true term by term for each side of the k, then that means that the coefficients can be equated, right? So that's what we're going to do, is just going to write this down, and then the coefficients themselves need to be equated. So I'm going to write that down in the nicest way possible. I am going to write this down. And put the sum out in front. So we did this really nice relabeling scheme. And I want you to kind of like stare at this and make sure it makes sense that these are equivalent statements. So here we have the thing itself, right, times kappa minus 1. Here we have the thing itself times kappa minus 1. Here we have minus 2 kappa times prime, and then we pull this thing out from the prime, but we shifted it. And then, oops, so yeah, that is wrong. I do have a kappa plus 1 there, I think. Nope. And then here we have just h double prime, and then so we have h double prime. So there was some shifting to equate the kappas, and then a vanishing of one term. So the one that might be mysterious is the second term. So we had to shift again because there's another psi here. So what used to be the plus 1 became plus 1 minus 1 because we have another psi. So this is literally just plugging these things in and doing the same relabeling trick and a fair amount of algebra. So this is the asymptotic part. The exponential went away, just algebraic cancellation. That was really nice. And then this is what's left over. And just as you guys were able to tell me what those two coefficients were, this thing has psi to the k everywhere, right? If this is true for all psi on the real line, what needs to be true is that the coefficients themselves, so think about factoring out the psi. So what needs to be true is each one of these independent terms needs to vanish. So this is what this ultimately tells us. Is that 0 equals, don't even need a sum, k times k minus 1, ak plus 2. And then I'll write it out kind of the hard way, actually. 2k ak plus kappa minus 1 ak. And actually all the physics is in kappa. That was the only thing that has like physics coefficients. And this is true for all k in, so k goes from 0 to infinity. And we can actually rewrite this. Actually rewrite it in 2 steps. sure it's somewhere, but the whiteboard really needs like a kind of blanket erase. Okay. So finally, what we have solving the above equation, you know, this thing that isn't as impressive yet to you guys as it should be probably. And I always thought kind of differential equations was magical because, with the exception of maybe some techniques like integrating factors, but they're only for, you know, like linear second order differential equations or first order differential equations, is that a lot of what diffie-q came down to is just like writing down the answer. And it always felt like kind of non-scientific. So this is, in some sense, a scientific way of solving this differential equation. We would have gotten a grosser recursion relation if we didn't have the foresight to pull off the asymptotic behavior. But this is the way it works, is that you tell me, for instance, A naught, right? And honestly, you can just pick that. And then I can tell you A2, and then A4 and A6. So it turns out that the way this would work is that I know AK plus 2 given AK. So for instance, and this will be called the even solution, for obvious reasons, is that if you pick an A naught, I can tell you A2 through this recursion relationship, and then that tells me A4, and then all the way up. And if you want an odd solution, you pick A1, and then I tell you A3 through the recursion relationship, and then that gets us A5, and so on and so forth. And then these will look like this. So remember, this is finding the values of the non-asymptotic part. Or if you want, you could sum over K. Or the odd part. So before doing an actual example where you would see this naturally, there's a little bit of a problem here. But you know, technically we have a solution, a method to get a solution, is that you just start with some coefficient. And it turns out that if you start with some coefficient equal to 1, you know, if you look at how this formula works, it would just, that's going to be your scale factor. You know, if you choose 1 for A naught and I choose 2 for A naught, we're going to make the same solution. It's just mine's going to be twice as big as yours. And the way that we would correct for that is by, you know, normalizing the function itself. So I see a little bit of a problem with this before we really get into it, is that this thing has kind of a scale issue, is that the upstairs of this kind of goes like K, right? So just to be clear, because I got a little bit sloppy, that's kappa, that's our physics constant, and that's K. So our upstairs kind of goes like kappa or K, and our downstairs goes like K squared. So this whole thing goes like 1 over K. What is the solution or approximate size of 1 over K as K goes from 0 to infinity? Think about it. Yeah.
Oh, it goes to 0.
The terms, yes. What does the sum of the terms do? Think about integrating 1 over x as x goes from 0 to infinity.
The whole sum might still diverge.
Yes. So there's an issue where we have divergence. So this actually diverges. So there's a way of stopping this from diverging. What would happen if, for instance, A10 was 0? So A10 is 0, and then I multiply it by the coefficient. What's A12?
It's also 0.
Yeah, and then A14 and A16, likewise for the odd solutions. We have two possibilities. One is that the series is so smart that it cuts itself off at some finite value, or we have this thing blowing up. Obviously, because we're talking about this, the series will cut itself off and we don't have a divergent series. So this thing is really smart. And you can see in the numerator how this would actually work, is that at some point, for some finite value of k, the numerator vanishes, and once the numerator vanishes, it stays vanished. Okay. So we have two options. One is that this thing diverges. This thing does not diverge. So for some finite value, and honestly, this is the part to me that's like really kind of mind-bending in some sense, is that when you talk about discrete spectra and the structure of the simple harmonic oscillator in quantum mechanics, purely from a physics lens, through a physics lens, it's like, yeah, this thing has to have some finite number of lumps, or it's got to obey boundary conditions. Is that this is the exact same thing showing up, but just purely through mathematical considerations. Is that if this thing has a solution, then it needs to have the following be true. For some finite value of k, the numerator of this thing, we'll call it double star, vanishes. And then the series is done. And the way that that would need to work is if kappa, which remember had all our physics goo in it, is equal to 2k plus 1. So once k is equal to kappa minus 1 over 2, then we're done. Or we'll call it k max equals kappa minus 1 over 2. And then we had some like physics stuff in there, right? So going back to what our definition of kappa itself was, that was equal to 2e over h bar omega naught, and then minus 1 over 2. It's a little bit weird, but that's what it means. You could solve this for e. Which looks maybe familiar to people who have seen the simple harmonic oscillator. But that's just the condition that this thing actually needs a solution. Okay, so we'll talk a little bit about it, but this is a generic feature of using the method of Forbinius, is that depending on what the recursion relation looks like, if the recursion relationship has two derivatives or fewer, this is going to kind of generically be the case, is that there needs to be some finite value where it truncates. Okay, so let's try this and see how it works. But any questions about that? So let's actually make a solution of the time-independent Schrodinger equation for the harmonic oscillator. So this is the whole point. So we'll make one together, and then I'll let you guys make one. Okay, so what we have is a k plus 2 is equal to 2k plus 1 minus kappa over And I'm just going to call it k equals 2k max plus 1. So let's not worry about physics constants. Let's just say that there's some max value where this thing dies. Okay. So I don't know. I'll do n equals 0. Should have been calling it k. So we'll do k equals 0. So do k max equals 0. It's really bold of me. So that means that, and let's do what people typically do is call k max n. So that means that 2n plus 1 minus kappa equals 0. So this means that for n equals 0, kappa equals 1, right? So this is the energy of the solution that we're finding in the quantum mechanical way of viewing it. So the way that this would work is that I just write this down. And we might start with AK equals 0. So A naught would satisfy 2 times 0. Well, looks like we're already done. Over 1 times 2 would tell me A 2. So honestly, A2 is vanishing. Like we already have the 0. And A naught is constant. Doesn't matter what it is. So for our first solution, A naught is constant, and then immediately the series truncates. A naught is constant, A2 through infinity are all 0. What a wonderful series. Okay, what does this have to do with the solution? Okay, so we know that the non-asymptotic part of this is equal to some k goes from 0 to infinity. We're not going to get it all the way there, obviously. AK squiggly k. But honestly, it's just a 0 and squiggly 0. So that's just a 0. And therefore, the whole solution, I mean, this is like the triumphant moment where we solve the thing, is A naught, and then we put the non-asymptotic piece back in. Okay, and usually what you do is you choose A naught to make sure that this thing is normalized. So make sure that we have this being true, which is the same thing as this being true, because we just rescaled our variables. Oops, dx. Which means A naught should be equal to pi to the -1/4, as it turns out, but sort of an aside. Okay, that was too easy. Why don't I make you guys do k max equals 1. It's not that much harder. Okay, so this is how the logic would work for that. We want our next solution. This is going to be an odd solution, which has to do with the numbers and the parity of the function itself. So k max equals 1. So what happens if I put 1 in here? That becomes 3. 2 times 1 plus 3. Let's do that in 2 steps. So 2 times 1 plus 1 minus kappa equals 0 means that kappa in this case needs to be equal to 3. So we put that into our recursion. So that's kind of like picking the energy that you want in your harmonic oscillator. And now we would start with a 1. And what does a 1 have to do with a, in this case, 3? So that would be 2 times 1, because k is 1, plus 1 minus 3 over 2 times 3, but that's still equal to 0. So just like k max equals 0, we have one solution, one term in the solution, then everything else vanishes. For k equals 1, we have one term in the solution, then everything vanishes. So that means that this is true, is that this is a 1, okay, slight difference is that psi to the first power. And then the entire solution would be a 1 psi times the asymptotic piece that we peeled off to make our life easy. And we would subscript this by psi 1, so the first excited state. Okay, if I plot this, it looks like the following. So it still has this dying exponential asymptotic behavior. But in the middle, it goes from negative to positive. So it looks like this. So this would be psi 1, whereas psi naught looks like this. So just an exponential. And then, you know, if you're clever, you can figure out what psi 2, psi 3, psi 4 is. So that's the method of Forbinius. The things that we've generated are called, the H parts are called Hermite polynomials. They have a lot of properties that you'll find to be very familiar. So we'll talk about that on Thursday for a bit. You can probably do all the homework just by looking up the properties in Arfken and Weber, honestly. But I want to talk about them again in the context of physics a little bit more. And as such, I moved this homework to being due on Thursday night. Could make it Friday too, honestly, just to go over that last problem.